Welcome to the session. Greeting of the day. In today's class, we are going to discuss about the electron beam welding process. In previous classes, we have discussed about the various welding process with respect to heat source, how it is developed. We have seen about the gas welding through gas, arc welding through electric arc, resistance welding through resistance heating, and solid state welding through mechanical conversions, and chemical reactions of thermochemical welding process. Now in the last radiant energy process, we are selected to study about this electron beam welding process, where the radiant energy is electron beam, which is to be emitted and is to be generate velocity of heat, through which we are going to do welding process. So electron beam welding, and we are going to talk about the total radiant energy. Why not those heat sources of gases? Why not those electric arc? Why not those resistance heating? Because the intensity of heat are higher, or developed heat inputs are higher than in those various processes. In this electron beam welding and laser beam welding process, very high intensity of beam of electromagnetic energy of electron and photons are generated. Through this, what we are doing, an important factor in the welding is heat input, that we know. We need a heat input to melt the workpieces. This has maybe a good or bad effect. What is this good effect? Good effect is melting and depositing and penetration. What is the bad effect? Due to this high heat input, there will be chance of creation of high heat affected zones, and also distortions will happen. So due to we want to avoid this heat affected zones, which is a brittle zone, and also distortions, it will bend the entire geometry of the weld specimen itself. Therefore these things to be avoided. So good is we are welding join, that is okay, but in the bad effects of a heat affected zone and distortions are found. Need high heat input to melt, that is okay. But what happens, high heat input will cause a more heat affected zone, that is a heat affected. And in the workpiece, what we want is, what we need enough energy focused at the gap where we want welding. Therefore we need enough energy focused into small area rather than spreading out. How we are actually doing in the welding process? How we are doing, you see, the electrode has been taken and the welding of workpieces is there. It is spreading over here. It is spreading over here. This is the spreading region. This we don't need. Actually what we need, the specific point we need there. The specific point we want to weld the specific gap. How it is generated? Here we want to make the welding process in this way. Simple. So this intensified specific point heating can be done by this electron beam welding and also by the laser beam welding process. Therefore this intensified heat is required in a small zone, not in the broad area. So therefore we need enough energy to be focused in a small area rather than in the spreading or maximizing the weld efficiency. So that is what we should do. Energy density is the best way to describe. So what now, the further I am going in this process of laser and electron beam welding, I am describing the hotness, the warm-up conditions, the temperature we need to welding process. I am describing it in the energy density for welding process, which is measured usually in the watts per meter square. Other factors to be considered are energy losses during the welding process. So these are atmospheric contaminations to be avoided, atmospheric air circulations in between the electron flow, that is to be avoided, those things to be taken care. Which can be measured, energy losses are heat transfer efficiency for welding process, low efficiency factors of 0.25 and high efficiency of 0.9 can be obtained. So very high intensified beam of electromagnetic energy. So what is the principle now? We came to electron beam welding process. Now we entered. Up to now we have seen, we have described the hotness and electron density. how we have intensified heat we are measuring. Watt per meter square. So principle, the heat, the heart of the electron beam process is the electron beam generation from the electron gun, that is column. We are going to generate the electron which is here in the electric arc welding process. Also the electron flow takes place from negative to positive. That is so we have taken care of direct current electronegative, direct current electropositive, those things we have did. The similar pattern of supplying of electron with high velocity also we are doing here, but only the source of tungsten and emission of electron and complete electron to travel directly towards the workpieces. That we are trying to do here in the electron beam welding. The electron beam welding using a small gun. Electrons are generated by heating a negatively charged filament. That is what tungsten filament we are using, because tungsten having the high melting point, and at higher when the temperature is increased on the tungsten, the kinetic energy of electrons are higher and it is released out from the tungsten and it attracted by the anode. It means the positive side. So filament, the cathode, to its thermoionic emission, when there is a critical temperature or it is increased over there, the emission of electron takes place. Temperature range upon which electrons are emitted. After emitting, what we are doing? It is to be focused towards the workpiece where the heat needed. Therefore, these electrons are accelerated by the electric field by negatively charged bias electrodes located between the cathode and the anode. We are focusing there. The electron beam can be focused under, very importantly, vacuum. See, this electron flow can be disturbed by the atmospheric air circulations. When heat is generated with high velocity, electron flow takes place from one end to the other positive end. In between, let us consider the released electron having 100% of heat. This 100% of heat to be utilized for melting of the workpiece and welding. But what happens in the middle, the atmospheric air circulations also come into the action and it disturbs this electron flow, and maybe this heat will be absorbed by this atmosphere. Therefore, we have to protect the electron flow under the workpiece from the atmospheric contaminations. Therefore, we are using a vacuum chamber where the gun, where the workpiece, the entire welding process takes place in the vacuum condition. Until now, the entire welding process we have not talked about this vacuum point. But here for electron beam welding, to intensify heat, we are planning to make the vacuum chamber working environment. Vacuum and strikes the metal surface at a velocity up to 70% of the speed of the light. Very important point. About 95% of the electron kinetic energy is converted into heat. Whatever the electrons released from the tungsten filament from the cathode, it comes down to the positive. So whatever it is released, it is not at all disturbed by the atmosphere. But in the plasma arc welding also electron released. TIG welding also electrons are released. But there we have protected the environment with respect to shielding gases. There is a chance, even though some forceful air is applied from the atmospheric side, there will be the disturbances. But here what we are using? The vacuum chamber we are using, therefore there is no chance of disturbances. Therefore obviously the electrons, whatever it is released, are converted into energy format of heat. That is what we are telling. 95% of electrons of kinetic energy is converted into heat format. So if it is 95% is converted heat to part of the working condition, efficiency will be 100%. There itself we have told we have 80% of thermal efficiency we are building, but here we can able to 100% we can able to achieve. The electron beam can be focused on the diameter in the range of 0.3 to 0.8. Very minimum gap can be welded. What means there is no need of edge preparation here. So what I am doing, we prepare edge preparation in such a way the electrode diameter, the electrode thickness, like this thicknesses has come down to the 0th mm and welding. But what I am doing, we are going to operate electron. There is no electrodes. There is no filler wires. Therefore, I am keeping the gap, 0 gap like this, and then I am passing the electron flow here with high velocity, which is 70% the speed of light, it impinges over their downward direction. Therefore, this specific location will be heated and then welding can be easily done. Therefore, what is it? The diameter in the range of 0.3 to 0.1 mm can also be welded. One key feature is that the ability to perform deeper penetration welding with the keyhole mode. What is it? Keyhole mode. This is keyhole. The high velocity is impinging over there and going downward direction specifically. We are not having arc length or this broad distributions are not there. The broad distributions of arc are not there. Therefore, we can specifically point its location. Specifically, the electron flow will happen, intensified heat and comes down and makes a simple looking like a keyhole method. So this is how that keyhole is performed in the actual photograph. See, here the welding has been started. The welding has been started from here. It started from here. There is a workpiece here and there. You see, workpiece here and there. But it is a total thickness of 19 mm. See how large thickness is this. But for this large thickness in the electrode welding or submerged arc welding, we should prepare a large V gap. And then we should come down to the 0th mm of electrode and then we should do welding. But here, electron with 70% of high light speeds, we are supplying with a high kinetic energy. The electron with the heat comes down and impinges from there. It is a setup, electron releasing tungsten setup, and it comes down and hits throughout with the heat going with high speed and it is joining there. And there, this heat is itself sufficient to make this process of welding methods. Therefore, there is no much more heat also involved. We need enough heat that is given with high speed. Therefore, enough heat is involved here to impinge over to the downward, and in the specific time, rapid solidification takes place in such a way welding occurs. There is no or very minimized heat affected zone, which is heat does not distributed. But what we are doing in those submerged arc welding process, heat is applied slowly, which means electron flow may be not at high speed. Therefore, heat is falling down. Heat is falling down. It is absorbed here. It is absorbed here. It is absorbed here. It means that the entire workpiece itself absorbing the heat. But here, due to this electrons of speed, you can able to impinge quickly towards the 0th point, and we can able to weld it quickly. Therefore, there is no chance of heat distribution throughout the workpieces. Therefore, a narrow HAZ or minimum nil HAZ we can able to achieve in this laser beam welding process. So see how far it is deep workpieces. It is so for example, two images are kept nearby, but this is 19 mm. But there, this is another photo which belongs to 102 mm. 102 mm. Imagine that how. High energy density of up to, how I have told you, initially I have told you this hardness are measured in the density of energy density in terms of up to how much we are giving. 110 watts per meter square we are giving the density to the fusion welding process. Here it is melting. It is not a solid state joining process, it is a fusion welding process. Bombardment of intensity beam of electron on the targeted material. Instantaneous conversion of kinetic energy. It means due to kinetic energy, the electrons are converted. This kinetic energy are instantaneously converted into this thermal energy due to its releasing speed and comes towards the downward. Bombardment of intense beam of electrons on the targeted material. Impinging of the electron causes weldment interfaces. It means this interface region. So we have two specimens here. This interface region, interface to melt and produce the weld joint. We are specifically applying high velocity of electrons here to impinge downwards. So this is the setup, which diagram we are getting some clarity. See, we have a high voltage cable which is connected to 30 kilowatt direct current, and then through that we are applying this 108 watts per meter square energy density we are going to create. Let's see the filament, the cathode grid, which is this, it means this is a tungsten filament here. From the tungsten filament, due to this application of 30 kilowatt voltage supply, power supply, the electrons are emitted. So this brown borders represents the vacuum condition, the welding as we are going to do in the vacuum table, vacuum chamber. So electrons are released from here, and it is focused where it will go. It will be attracted by the anode, positive, negative to the positive conditions. So it is focused there. While it is coming down, we are attracting by the magnetic fields of magnetic lenses, deflection coils, and therefore it is converged towards one end, and I am focusing the same towards the workpieces. Therefore we are achieving the 70% speed, velocity of the light. So then it is impinged towards the downward direction where we have the workpieces at the bottom. All takes place in the working chamber of vacuum. Therefore here it is impinged. In case I am having the two specimens here, one specimen this one and one more specimen this one. Therefore I want to make a keyhole welding, not a broad this some of the high heat input, large heat effector zone, nothing else it is there. High impact takes place, in immediate the keyhole row zone will be melted and welded. Very simple. But we have to make the condition of vacuum chamber, or otherwise what happens? The speed we will not achieve. If vacuum is we have removed, even though in the TIG welding process, vacuum we have not used, but shielding gas we have used. The same condition, if you are using the vacuum is removed, the atmospheric environment contamination will take place, and this high velocity will not be achieved, and therefore this keyhole welding cannot be achieved. Therefore we are going for vacuum to achieve this keyhole specific point welding. No electrodes, no fillers, no shielding gas, nothing we are using. Just electron, high speed, vacuum, 100% of utilization of the electron releasing with high speed. The electron beam gun has a tungsten filament. Now only we have told you, which is heated, freeing the electrons. Now the electrons are freed. Electrons are freed now. The electrons are accelerated from the source. It means tungsten filament from the source with high voltage potential between the cathode to the anode. This stream of electrons then passes through the hole in the anode. This hole they are talking, this hole in the anode. And the beam is directed to the magnetic forces of the focusing and the deflection coils. And it is focused towards the magnetic lenses and deflection coils, through which we are accumulating the lens water, the electron released to the single point. That is what these lenses and deflection coils does the job. These beams are directed out to strike the workpieces. The kinetic energy of electron is transferred to heat. When it is kinetic energy comes with a high velocity, it generates automatically heat because it is impinging those regions. Heat upon impact of the workpieces and cuts the perfect hole and the weld joint, makes the hole there. Accordingly, when it is solidifying, the other fine surfaces will be comes down and welded. Molten metal fills, therefore, after that, this molten metal fills behind the beam and creating the deep finishing welds. Deeper penetration, we have seen one image of 104 mm, one image of 20 mm specimens can be welded. So maximum we can able to do deeper penetration with high velocity of electron, we can go downwards. Without a narrow heat effector zone, no minimized heat effector zone. So we can able to computerize it for the temperature controls, we can able to do. So this is a fusion welding, heating caused by electron beam to the tungsten filaments, and with a beam focus of 0.8 to 3.2 mm. Minimum gap, less than 1 mm gap can be welded. There is zero gap. Surface polishing is most important there. If you are giving gap and welding, electron will go downwards, no welding will occur. Therefore, we should two specimens to be kept perfectly without the gap. The gap to be maintained zero. The welding itself 1 mm. 2 mm. One the welding, the electron dimension itself 1 mm. Therefore, 0.8 to 3 mm gap will be there. Can produce the high temperatures. Must be used in the hard vacuum up to 10 to the power minus 3 to 10 to the power minus 3 atmospheric condition to prevent electron from the interacting with the molecules of the atmosphere. See, very important. That's the point I told you. To prevent the electron from the interacting with the atoms or molecules in the atmosphere. Otherwise, what happens? This electron which is released from the tungsten will interact with this atmosphere. That's a problem. Then heat will be reduced. Intensified keyhole welding cannot be done. So that is therefore but these are some hazards are there. This electron releasing also generates the X-rays, which is somehow it is harmful. Therefore, to be taken care. Keyhole formation. The power density of this process is higher than that of 109, 108 watts per meter square. The same point we have seen there also. As consequently of high energy concentration, the mechanisms of weldable from the formation is somewhat different from the normal fusion. In joint area, the material is heated to very high temperature and may vaporize. This keyhole method is going to vaporize the specimen. Then where it will transfer the heat? Transfer of heat when the material is there, then it absorbs and transfers. But this high intensified 109 watts per meter square, what happens? It is vaporizing the whole. The material is not there. The surfaces which are nearby is later it is filling the gap. That is how we are intensifying doing. The deep crater of hole is formed immediately under heat source. A reservoir of the molten metal is produced behind this keyhole. Therefore, the reservoir of molten metal which is at the surfaces, at the sides, are going to come down and it is melted. But we are preparing a 0.1 mm intensified heat and we are removing the vaporizers. There also vaporized material is gone inside, but the surfaces are absorbed other than that of vaporized temperature. Then those temperatures are filling the remaining gap. As that is what reservoir molten metal is produced behind the keyhole. As the heat source moves from forward, the hole is filled with the molten metal from the reservoir. This solidifies to form a weld beam. This technique is known as a keyhole formation. So, through the electron beam welding process, we are generating the keyhole method. Variables what we are using importantly the primary variables are filament current voltage to emit electrons. How many current supply you have to give in such a way electrons will be high kinetic energy and then it is emitted from the tungsten. Then it is towards the workpiece we are projecting. Travel speed, how much travel speed needed, and then secondary variables maybe where we are focusing, what is the deflection, power supply, how much power supply, the 30 kilowatt or 50 kilowatt supply, how much we are giving, and then the vacuum condition, how much vacuum condition we are protecting. So these are the primary and secondary variables to be taken care. So you see, I have compared some various with respect to this fusion zone of various welding process. You can able to see in the flux core arc welding process. Flux core arc welding process, we have done the welding process of this broadness we have received. Similar to the gas welding also. The similar pattern of width and penetration happen. But in the plasma, you see the plasma, when we are supplying the high current, because this plasma is electron flow, plasma is specifically plasma generated and the two nozzles are there, protection nozzle, plasma nozzle. Through that we are trying to create the depth of, increasing the depth of penetration. And similar to the electron beam now, what we have studied, see, similar to that again with the focused beam. With the focused beam, a defocused film. With the defocused film, we can weld. With the focused film, keyhole welding. So we can able to try to make the keyhole welding process. We are achieved keyhole welding in plasma arc. At the same time, we are achieving the electron beam welding also. Okay. So the advantage limitations, you see, the advantage is what we are doing. It may be thin material, it may be thick material. Thin or thick materials from 0.025 mm to 300 mm. We have seen one image of 104, but here we are mentioning up to 300 mm also. keyhole welding possible by electron beam welding process. Accurately controlled density, computerized density, how far it is, 109 kilowatt per meter square we can able to apply. And a small beam, size also small, 1 mm, 0.8 mm beam can be, rays can be focused towards the workpiece. Therefore we are getting keyhole. Accurate beam alignment at any positions, wherever we need, we can able to align computerized, optimized vacuum chamber, we can able to do. Low total heat input, so narrow heat affected zone, because the focused heat are applied only to vaporized and only to melt, and there itself it is going to weld. This heat is more than enough to do the same job. It means only heating and welding the specific location. Therefore there is no distribution of heat, no absorbing of heat towards the remaining other heat affected zones are not formed. Therefore until narrow heat affected zone. Therefore if heat affected zone is not there, obviously low resistance stress is not generated, and therefore if the stress is not generated, distortions also we can able to avoid. So these are some of the very good advantages regarding the electron beam welding. No distortions, no metallurgical impact on the microstructure. It means there is no martensitic formations and other changeovers are not occurred. So those are the vacuum welding protects from the surface contaminations. See, atmospheric contaminations not there as we are using the vacuum. So these are some of the dissimilar weldings can be done. Therefore dissimilar welding and the secondary operations not needed, because there is no flux generated, there is no flashes, there is no removal of spatters, nothing else is there. Therefore secondary operations not needed. Limitations: it is a rapid solidification. Intensified heat supply, intensified immediately solidification. Therefore there is a chance of brittleness, there is a chance of this defects of other porosities, some other defects will be formed. Vacuum chamber may reduce the product size and limit. What is this? If you want to weld a large lengthy job, we can't able to do. It means we have to perform a large vacuum chamber. Equipment cost will be high. Converting this room into vacuum, it is a difficult job. So that it increases the cost. So vacuum chamber preparation reduces the limiting ourselves with respect to size, as because it can't able to perform the vacuum room. Electrical conductivity of the material is required, because we are supplying electrical supply from negative to positive. It should be conductive material. If non-conductive material, where the electron will reach, where it will be absorbed, where is cathode, where is anode. Therefore electrical conductive material to be there. X-ray formation is emission of secondary electrons from the workpieces. Therefore some problem of X-ray formation will be there. Very difficult to be handled carefully. Very high cost. So why it is high cost? As because it is vacuum. Obviously it become high cost. So the applications, the typical applications of electron beams of welding are, you can able to weld bimetal saw blades, some dissimilar weldings. I can able to tell dissimilar metals welding. And then transmission assemblies, where we have to reduce heat, because if the heat affected zone is formed, then it all will be failure. Brittleness will be there. Therefore it should not form this transmission assembly system. We should not form in there, because that is an important part, sir. Aerospace components, here also brittleness should be avoided. Brittleness to be avoided. Therefore in such cases we are using this electron beam welding methods. So summary: in welding we have seen about in the radiant energy process, radiant energy, we have seen about electron beam welding. in this electron beam we have seen about keyhole method, and also we have seen about advantages, disadvantages and applications. The remaining part of the subjects, see you in the next session. Thank you.